condensation. So let's start with the retrosynthetic analysis problem. Here is a compound that perhaps sparks us to think about a synthesis based on the Claisen condensation. So the key feature here is that we have, if this is the ester carbonyl, we have the position alpha to the ester, and then the next carbon over would be beta relative to the ester carbonyl. At the beta carbon, we have a ketone group. So this is a beta keto ester. And for a beta keto ester, we should think about the Claisen condensation in terms of a way to make this compound. So the first problem is to dissect this beta keto ester in a retrosynthetic manner, decide what the key bond disconnection is, and see if you can work this back to the starting materials for a Claisen condensation. Remembering, if you need a hint, that a Claisen condensation involves the addition of an ester enolate as the nucleophile to the carbonyl of a second molecule of ester. The key bond disconnection in a Claisen condensation retrosynthetic analysis is between the alpha and the beta position. And so this portion, the left-hand side portion as drawn, would come from one ester molecule. And then in terms of what type of ester I should use, I don't want to make things too complicated. So if I have a methyl ester in the final product, let's not make things more difficult than they need to be. So let's make this a methyl ester as well. So that would account for the carbons on the left. That is destined to become the beta carbon in the final beta keto ester product. And then these carbons here will come from a second molecule of ester. This will be the portion that acts as the nucleophile. And I mentioned we want to have an ester enolate, so I will draw that ester enolate in this way. Remember, the reason it's okay to have a negative charge on carbon is that this negative charge is actually resonance delocalized into the ester carbonyl. So these would be the two reactants that I would need in order to get to the desired product. So now this compound is a reasonable starting material. It's an ester that I might be able to buy. And then this thing, this enolate, the question is, where does this enolate come from? Well, this enolate should come from the corresponding version of this molecule that just has a proton still at that carbon. So to complete the retrosynthetic analysis, there would be the second ester that I would need. And fortuitously, it looks like, so here's the alpha carbon that's going to end up in our final beta keto ester product. This ester and this ester are identical. So that makes the reaction easier to do because we don't have to worry about crossed Claisen products. Both components are the same starting material. All right, so the next thing, the next part of this problem, we have done the retrosynthetic analysis. So we're going to use this ester as our starting material. Propose conditions for doing this synthesis, and also write a mechanism for the formation of this beta keto ester from this starting material. Okay, so we want the reaction conditions, and we also want a mechanism. Before you launch into that, let me just point out one thing that we were at pains to show in class, And that is that this beta-keto ester product has at least one hydrogen in this case, at the carbon in between the ester carbonyl and the ketone carbonyl. Remember, for a Claisen condensation to be thermodynamically feasible, we need to have that feature of the beta-keto ester product that we're trying to make. Okay, so back to this. Propose conditions for carrying out this Claisen condensation and write a mechanism. All right, here was the ester that we decided we should use as our starting material. And let's focus on the alpha carbon. There are 2 hydrogens here. So again, because one of the hydrogens is lost when we make the enolate, and we must have one hydrogen left at this position in the final product. Remember that Claisen condensations are really only feasible when your starting ester has at least 2 alpha hydrogens. So this meets the bill. In terms of the reaction conditions, we should pick a base to make the enolate that corresponds to the OR group of the ester. In this particular case, we would use methoxide as our base. Let's say it's sodium methoxide. And then the typical solvent is the corresponding alcohol, the conjugate acid of the base that's being used. So in this case, we would use sodium methoxide in methanol. And the final product is our beta-keto ester, except, remember, and we'll work through this mechanistically, under these reaction conditions, the actual product is not the final product that has 2 hydrogens here in the middle. It is a final product that only has 1 hydrogen and has a negative charge. And this negative charge is delocalized into the ketone carbonyl, and it's delocalized into the ester carbonyl. And then at the end of the reaction, so really the Claisen condensation involves an initial base-promoted condensation, but then there has to be a workup in which we provide some protic source to protonate this final enolate product. So the final, I'm sorry, here, hold on. That's not a hydrogen. That's that, okay? And then the final product after workup will be that, okay? So let's work through the mechanism of this Claisen condensation. The other thing is, of course, if we're going to really balance the equation here, we need 2 equivalents of the starting ester to make 1 molecule of the final beta-keto ester product. So how does this work? Well, the first thing we need to do is we need to deprotonate the ester. So we're going to use the base, methoxide, deprotonate to make the ester enolate. So there is the ester enolate. Remember, given the pKa of a hydrogen alpha to an ester, which is maybe in the range of 20 to 21, and given the pKa of the conjugate acid of the base that we're using, the pKa of methanol is maybe about 16 or 17, really the equilibrium favors the starting ester, so we really are only going to make a little bit of the enolate. And that's good, in fact, because we need to have some of the ester that is not in the enolate form because that deprotonated ester is going to act as our electrophile. So now here's my alpha carbon. Here's the carbon that's destined to become the beta carbon in the product. The enolate adds to the ester carbonyl, and we make a tetrahedral intermediate in the usual way. So at this point, I have joined the two pieces together. There we go. Tetrahedral intermediate. This tetrahedral intermediate can collapse. At this point, we could eject methoxide and go back to where we started. We could eject the enolate and go back to where we started. Or we could eject methoxide and go on in the direction of product. So let's show that. So this gives us the keto group at the beta position. Here's beta, here's alpha. We also have the methoxide that left in that step. So at this point, we have a beta keto ester product. The methoxide could add back into the carbonyl of the ketone, and that would take us back to this tetrahedral intermediate. So again, we should think about the thermodynamics of the process so far. Because so far, I have traded two ester carbonyls from the starting material. So I had 2 molecules of ester, so 2 ester carbonyls. I still have one of the 2 ester carbonyls, but the other ester carbonyl is no longer with us. It has become a ketone carbonyl. This is a thermodynamic problem in terms of this relative stability of what I have here versus what I had to begin with, because a ketone carbonyl is less thermodynamically stable than an ester carbonyl, so I've given that up. So the thing that really drives the reaction through to completion in the forward direction is the next step, because the next step pretty much irreversibly leads to deprotonation of this hydrogen at the alpha position. Remember, because this hydrogen is between 2 carbonyls, its pKa is relatively low. So this is a relatively acidic hydrogen. So this hydrogen has a pKa of about 11. When methoxide removes this hydrogen, it gives this anion and methanol. The methanol has a pKa of about 17. So this final deprotonation under the basic reaction conditions is what drives the Claisen condensation to completion. If it weren't for the fact that we had this 1 hydrogen left to deprotonate, really the equilibrium would have favored the starting materials. So at this point, we have this compound right here. And then if we do a workup and quench that anion, we end up with the final product. All right, so practice working through the mechanism of the Claisen condensation. Remember the limitations in terms of what type of esters can productively undergo Claisen. The starting ester must have at least 2 alpha hydrogens. And the reason is that at this point, by the time you get to the beta keto ester, one of those hydrogens must remain to be removed in this reaction driving step. So this is the reaction driving step right there.